So before we start looking at all of the different conformations in the Newman projections for N-butane, I thought I might try to give you a bit better visualization of how these Newman projections look. So I'm using a program called the Atomic Dashboard. For those of you who have Macs or MacBook Pros or iPads, these are all available as apps. I believe it's a $15 app. And you can build several different types of molecules. So this one's N-butane. Notice, as I discussed earlier, on carbon 2, and I'm going to call carbon 2 the one to the left, you have a hydrogen atom that goes into the plane of the screen away from you. You have a hydrogen atom that comes out of the plane of the screen towards you. You have a carbon that's in the same plane as carbon 2. And you have another carbon that's in the same plane as carbon 2. So in a Newman projection, what we're really going to do is look down this bond axis where we can see carbon 2 directly. And so I'm looking directly down the bond axis. The hydrogen that was coming out of the plane of the screen is now up and to the right. The hydrogen that was going into the plane of the screen is now up and to the left. And the methyl group that was in the same plane as carbon 2 is still in the same plane as carbon 2, only now it's going straight down. Notice this is the lowest energy conformation for butane because the biggest, bulkiest group on carbon 2, the methyl group, and the biggest, bulkiest group on carbon 3, which is also a methyl group, are 180 degrees in terms of their dihedral angle, one from another. This is the lowest energy conformation that one can obtain for N-butane. If we hold this back carbon steady and begin to rotate, we can obtain a rotamer in which we have the methyl group with a 0 degree dihedral angle. So you need to use your imagination just a little bit here. So this methyl group eclipses on this methyl group, and this hydrogen eclipses on this hydrogen, and this hydrogen eclipses on this hydrogen. And that's the highest energy intermediate that we can have. So we call these rotamers because we obtain them by simply rotating around the C2-C3 bond. So now let's go in and draw all of these different conformations. And I'm going to start with the highest energy. And just so that we're doing the same comparisons as last time, here is our parent molecule. I'm probably going to mess up the color scheme, but I'll do my best to keep it the way that it was. And again, carbon 2 and carbon 3, just so that we're clear. Of course, these guys are also carbons. I'm actually going to label 2 and 3. And I am looking down the bond axis of C2, C3. So when I draw the lowest energy conformation, which is where the dihedral angle will be 180 degrees. Having some issues drawing this straight. It's actually harder than it looks. And the three groups that are bonded to C3. Again, I would definitely suggest using a plastic model to build all of these so that this makes sense. This is quite difficult to do and just visualize in your mind's eye. So your eye is looking down this bond axis right here. And you're looking at C2. So here's C2. And you can't really see C3. It's a little interesting that we choose to show the atom that we can't see as the larger circle and the atom that we can't see as a dot that is in front. So this would be a 180 degree dihedral. So in class, when I refer to the dihedral, I'm talking about the angle between the two biggest and bulkiest groups. And we need to understand that a methyl group is going to be bigger than a chlorine, a bromine, an iodine, because it has more atoms. All right, so we could also do this for the Eclipse conformation. Again, I'm going to keep all of the back things attached to the back carbon steady, so I'm rotating the front carbon. You actually could do either one, but just so that we do this consistently, I think it's a good idea if we keep the back carbon steady, just so that we are consistent. In actuality, it doesn't matter if we rotate the back or rotate the front, as long as you keep one of them constant. And so I'm going to rotate this 180 degrees such that these two methyl groups exhibit a tremendous amount of crowding interactions. This crowding interaction we're going to call steric strain. And later we will explore mathematically just how much steric strain is associated with these two methyl groups having a zero dihedral as opposed to having them with a 180 degree dihedral. Now, also need to convince yourself that these two hydrogens will eclipse, and also that these two hydrogens will eclipse. And this is 0 degrees. Now, if we hold the back carbon steady and just begin to rotate, we can account for 60, 120, 240, 300. 360 is going to be the same as 0. And then we can map all of this on a graph. So let's start with 60 degrees. Again, let's keep all of the atoms attached to the back carbon exactly in the same conformation. Means we haven't rotated them. But what we will rotate is the front methyl group, and I'm seeing right now that I've already made a boo-boo on the second one. We should show this actually bonding to the front carbon that I've rendered as a dot. So let me fix that. Okay, so as we come over here, I now want my other methyl group to be 60 degrees rotated clockwise, and I'm going to do this with everything. That means now that my red hydrogen occupies this spot, and of course my green hydrogen occupies this spot. This is a 60-degree dihedral. Again, we're going to measure our angle clockwise and relative between the two methyl groups. This is a staggered conformation. Remember from the last podcast, I said we'll have 3 staggered and 3 eclipsed. I've already seen 2 staggered and 1 eclipsed. Also notice this is the highest in energy, this is the lowest in energy, and we can take the time to explain that in just a bit. The reason that 180 is lower than 60 is you have what we call gauche interactions. Gauche interactions. Those are slightly sterically hindered, not nearly as much as eclipsed. So all the gauche interactions I have in the 180 degree structure are methyl groups and hydrogens. That's much more favorable than having a methyl-methyl gauche. So the one that's lowest in energy, I'm going to call conformation number 1. The one that's highest in energy, I'm going to call conformation number 6. I do not yet know where to place this one in terms of relative energies. Okay, so now let's go to the 120. I'm just going to draw these all in a row. We got 120. We already have 180. We need 240. And we need 300. And in all of these, the methyl group is coming straight up relative to that back carbon, carbon 3. Hydrogen in yellow is down and to the right. Again, we're just wanting to be consistent. It makes analyzing these structures so much easier if you're consistent. You don't want to spend a lot of time on your question answering on artistry. So now we're going to rotate another 60 degrees. And so the methyl group from our front carbon is eclipsed with the yellow hydrogen. Our red hydrogen is eclipsed with our magenta hydrogen. And our green hydrogen is eclipsed with the methyl group coming from the back carbon. This is 120 degrees. Again, if we compare 120 to 0, the methyl-methyl eclipse is much worse than 3-methyl hydrogen, with 2 methyl hydrogen eclipses and 1 hydrogen-hydrogen eclipse. Again, mathematically, we can work on this in class. There are going to be energetic values that we can give, and I'll probably put that in a future OZCast. All right, we've already done 180, so now let's go to 240. So what we can do is from 120, we're going to rotate 120 degrees. And so now this methyl group goes here, the hydrogen in red goes here, the hydrogen in green goes here. Methyl group. Red hydrogen. Green hydrogen. Remember, this may not look eclipsed. It's because of our limitations in trying to show this on a two-dimensional screen. So I'll try to fix this a little bit so it looks a little bit like they're on top of one another. And this is going to be a 240 degree dihedral. Now let's compare the relative energies between these two. In both of these, I have 2 methyl hydrogen eclipse and 1 hydrogen-hydrogen eclipse. They are equal in energy. So I'm going to give them an energetic value of 4. Finally, let's look at 300 degrees. So I'm going to rotate another 60. So this will go here, this will go here, this will go here. And we want to compare this one to 60 degrees. I think what you're going to find is that 60 degrees and 300 degrees are also equal in energy. When you have symmetric molecules and you show the Newman, some of them are going to overlap. And of course, this is 300 degrees. And so these guys are the same. Equal in energy, degenerate in energy. You've got a methyl-methyl gauche, and you've got 1, 2, 3 hydrogen-hydrogen gauche, and you've got 2 methyl hydrogen gauche. And if you look at this guy, you've got the same thing. You've got a methyl-methyl, you've got 1, 2, 3 hydrogen-hydrogen gauche, and you've got 1, 2 methyl hydrogen gauche. So they're the same in energy. So now that we've drawn all these conformations, we need to rank them in terms of a graph. And here's how we're going to do this. You're going to have potential energy as a function of torsional angle. And so this will be 0, and I'm going to make a marking for every 60. 0, 60, 120, 180, 240, 300, 360. Of course, 360 is the same as 0. So at 0 and at 360, we have our highest energy. That's our fully eclipsed. And so you want to make these the same Y value, essentially. 180 is our lowest. You want to make that the lowest Y value. 60 and 300 are essentially the same. You want those to have the same Y value. 120 and 240 are higher in energy than the highest staggered, but lower than the eclipsed. So now all we really have to do is connect the dots. And then the cycle will begin to repeat itself yet again. Now, what I would do at this point is I've given each of these a number. So I can call this 1. I could call these 2, indicating that they're the same in energy. I can call these 2 4. I can call these 2 6. And now I have successfully plotted the potential energy diagram for all of the rotamers of N-butane. You will be expected to do this for a given molecule on exam 2. On your final, you'll be expected to know the proper Newman projection for the highest energy rotamer of a given molecule. You'll also have to convert from a terse structure to a Newman, or from a Newman to a terse structure, or from a Newman to a Fischer, which we'll talk about later. So you really need a lot of good practice mastering the material in conformation. So I'd like you to do the whole thing on this molecule. Let's do 2 bromo, 3 iodo butane. Draw all 6 of the Fischer projections. Rank them in terms of their stability. Draw a potential energy diagram. And so we can go over this on class, probably Wednesday in class. Instead of having lab, we're going to have to do the lectures so we don't fall ridiculously behind. And so I think if you can go through and work on this, it'll allow us to go through things a lot more efficiently. It'd be really nice if most of class we could just work a bunch of problems and I don't have to spend a lot of time giving you the background theory. It makes things a lot more efficiently, and I think that's where things begin to click for you all as well. Needless to say, we'll be talking about this next Sunday in our review session.